For decades, putting a satellite into space meant abandoning it. Once it left the launch pad, that billion-dollar machine was entirely on its own. Getting mass to orbit has gotten incredibly cheap, but once a satellite actually arrives in space, moving it to its final position or managing it over time remains inefficient. We solved the highway, but we're stuck on the last mile. Because there was no help coming, engineers had to build massive propulsion systems and heavy fuel tanks directly into every single satellite. Every pound of fuel you add is a pound of sensors, cameras, or communication arrays you have to leave on the ground. You sacrifice the exact hardware that generates revenue just to move it. And the moment that built-in fuel runs out, the entire asset becomes useless. It turns into dead space junk, even if the computers and sensors still work perfectly. Building a satellite to be completely self-reliant was once an engineering necessity. Now, for many operators, it is a devastating capital inefficiency. This chart compares the traditional life cycle to a new infrastructure layer, the Orbital Transfer Vehicle, or OTV. Modern rideshare launches change the math by allowing operators to split the cost of a single trip, but these flights drop everyone off in a single generic orbit. This creates a choice for operators: spend capital on internal satellite capabilities or outsource that work to a third-party OTV. A crowded market of space tugs has emerged to provide these services, with companies like Atomos, Firefly, Impulse, and Starfish already testing hardware. Relying on a third party introduces new mechanical integration risks. If the OTV fails, your payload is stuck in the wrong place. To navigate this market, operators need to categorize these vehicles by the specific business scenario they solve, rather than just their thrust specs. The first specific sector of the OTV economy covers last-mile delivery and tactical response. This matrix breaks down the ROI. In row 1, vehicles like Impulse Space's Mira operate as delivery vans for orbital payloads. The input relies on third-party thrusters for precise placement into MEO or GEO, allowing the satellite to stay small and light. Military and government planners are finding specific applications for these agile vehicles in tactical deployments. Space domain awareness missions use these tugs to monitor potential orbital threats, keeping primary mission assets out of harm's way. The trade-off is the added layer of mechanical integration. If the OTV fails, the asset is stranded in a useless orbit. For defense planners and bulk launch customers, trading that integration risk for precise, cheap orbital delivery results in a positive ROI. The second sector moves from transportation to on-orbit compute and infrastructure. Operators can offload power-intensive data processing to a persistent orbital vehicle, such as Firefly's Elytra. These vehicles integrate advanced commercial hardware, including NVIDIA Jetson modules, to act as flying server farms. This setup overcomes deep space downlink constraints by processing raw data locally and transmitting only the final intelligence to Earth. Firefly's Ocula lunar mapping service relies on this computing power to provide real-time data insights from the moon. The hidden trade-off is total reliance. Your core data pipeline depends entirely on the uptime of a third party's persistent infrastructure. For high-data lunar missions, trading data latency for third-party platform lock-in is a calculated necessity. The final service sector is end-of-life disposal, often called Deorbit-as-a-Service. Operators can contract vehicles like Starfish Space's Otter to capture and dispose of dead satellites autonomously. This is possible through Cetacean software, which uses a single-camera visual guidance system to navigate the approach. This approach eliminates the need for the target satellite to carry its own heavy, specialized docking hardware. As an outcome, operators can strip deorbit fuel from their satellite designs, maximizing their revenue-generating lifespan. The trade-off is trust. Autonomous operations near sensitive assets require absolute software reliability to avoid creating catastrophic debris. However, the $52.5 million contract the Space Force awarded to Starfish proves the financial logic for outsourcing orbital disposal is now solid. Success in the OTV market requires operators to rigorously match their specific mission to the right service. Constellation operators find their ROI by stripping out onboard propulsion and paying for third-party delivery and disposal services instead. Government and defense planners find their value in tactical responsiveness, using delivery vehicles to move assets quickly. Deep space researchers find ROI by leasing on-orbit infrastructure to solve their communications and data bottlenecks. Identifying your specific operational bottleneck is the only way to realize the cost savings of the as-a-service space economy. The traditional model of a massive, fully self-reliant satellite is being directly challenged by a much more efficient and cheaper alternative. Space tugs are becoming distinct contractible utilities, functioning like tow trucks, server farms, and delivery vans. This allows engineers to design vastly simpler and cheaper core satellites, now focused entirely on their primary mission. Major aerospace hubs are already actively adapting to this outsourced utility model. The next phase of orbital logistics shifts focus toward the services a satellite utilizes after launch, rather than just the capabilities built into the bus. Navigating the new space economy requires letting go of absolute mission control and embracing the efficiency of orbital outsourcing.